So in the second of our little sessions on electromagnetic induction, this is part 2. We're going to finalise some of the formulas for electromagnetic induction and also link it with Lenz's law. So we're going to develop Faraday's law to a moving conductor in a magnetic field to see why, explain more as to why current is produced, and then we're going to link in Lenz's law to explain why energy is required to move the conductor, and then we're going to derive equations for induced flux, flux linkage, and induced EMF. So Faraday's law of magnetic induction, this is the person we're going to bring in today. This is Lenz's law, and he added to Faraday's law to explain quite a crucial idea. Okay, this was Faraday's law. Just to remind you, if we move this conductor, if we move it, so we apply a force and we move it through this magnetic field, here my shaded blue circle is showing that the magnetic field is going into the screen. Then as we move this conductor through, an EMF is going to be induced in the conductor because the electrons are going to be forced down one end of the rod. You can use Fleming's right-hand rule, remember, to work out the direction. Remember, this will show you the conventional current, so if you use that on this diagram, then using your right-hand rule, the first finger is the field that goes into the screen. The thumb is the force, so the applied force is going to be pointing towards the right of the screen. So that will leave your second finger pointing upwards, which means conventional current will flow up, and hence I've got electrons moving down the screen. But what do we know about a current carrying conductor in a magnetic field? Well, we know that it will experience a force. So when you move this, it's going to have a force act on it. Now that force is going to act in the opposite direction. How do I know? Well, for this you can use the left-hand rule. So if you use the left-hand rule, knowing that the current is flowing up, like we've shown, remember the left-hand rule is the direction of conventional current. So if you use left-hand rule with magnetic field going into the screen, current flowing up, you should see that the force on this wire is to the left. So it opposes the applied force that you are putting in. So as you move the wire to the right, an opposing force tries to stop you from doing that and pushes it the other way. And it's an equal and opposite force, and it will oppose the conductor as long as you try to move it. Why is this important? Well, this is Lenz's law, and Lenz's law states the direction of the induced current is always such that as to oppose the change that causes the current. If you think in things we've done in the lab, when we pushed a magnet into the coil and it caused a current one way, then removing the magnet, it causes a current in the opposite direction. And that is something that you might be thinking, well, why does that happen? Lenz's law helps us to work out why this happens. If it didn't happen, then you might have a contradiction to the law of energy conservation. So if we just look at some pictures, this is us. If we move this magnet into a coil, then it produces a current in one direction, and then we move it out of the coil, it's producing another direction. This is the north pole. It was producing a current. This was anti-clockwise, and then when we pulled it out, it was a south pole. If we'd have done this test properly, you can see a north pole moving in will produce a north pole on the end of the coil with an anti-clockwise current. So this north will repel the north pole that's produced because of the current in the coil of wire. When we move it out, the north pole moving out, the current changes, so it's a south pole here, and that means you get a force of attraction between the south pole and the north pole. So as you're trying to move the magnet out, it's being attracted by the magnetic field that's induced because of the current. This can be quite confusing, so it's worth sort of taking your time and just thinking through everything on the diagrams on screen. But you can see that moving in, you get repelled. Moving out, you get attracted back in. This is a perfect example of Lenz's law, and it also helps you to realise why the energy is never created or destroyed. The induced current could never be in a direction to help the change. If moving this magnet in caused a south pole here, then this magnet would effectively be attracted in. So you'd almost have a situation where a magnet's being pulled in and you wouldn't have to push it, So you'd have a situation where free electricity is being generated because you haven't got to push in, you haven't got to use any of your energy up to push the magnet in. The magnet would keep moving in and generate electricity on the way, so you could almost end up with a free electricity machine. Okay, we need to just put an equation on Faraday's law of electromagnetic induction. Let's just look at this again. Here we've got our wire and it's moving in this magnetic field. It moves from this position over to this position and it moves a distance delta S. Here's the distance it moves, and it does that in a time t, delta t. The work done to do this must be equal to the force times the distance. This is our standard equation from year 12, force times distance. The force that we need to put in is given to us by the magnetic force of a conductor moving in a current carrying conductor of length L. So work done is force, BIL, multiplied by distance, delta S. So our work done is BIL delta S. The current that is transferred, or the charge that's transferred along this conductor, is actually equal to I delta T. This is what our charge is. I is Q over T, so Q becomes I delta T. So our charge transfer is Q equals I delta T. And induced EMF, if you remember from AS, EMF or voltage, if you want to call it that, is the work done per unit charge. So it's W over Q. So it's how much energy is transferred by how much charges. E equals work done per unit charge. So our work done was BIL delta S, and our charge is I delta T. Straight away you can see the I's cancel. So we end up with a formula that says the induced EMF will be equal to BL delta S divided by delta T. So this is the magnetic flux density multiplied by the length of wire multiplied by the distance it moves divided by the time taken to move that distance. Now this green square that's just coming up on screen, if I've got the product of L delta S for this rectangle, L delta S as in the formula here, then L delta S is effectively the area swept out by the conductor. What I mean by swept out is that the area it moves through, because as this wire moves from this position to this position, it sweeps out an area equivalent to the green circle. So I'm going to replace L delta S with A, meaning the area that the conductor sweeps out. So I've now got a formula that says the induced EMF is equal to BA divided by delta T. Straight away now you can see that this looks like the electromagnetic induction. The induced EMF of a circuit is equal to the rate of change of flux. So delta T means a rate of change, and we've got flux tied up in our flux density of B and our area of A. If we move this conductor in a magnetic field, let's just come up with one more equation. Here is just what we've just said. E equals W over Q, and we put in BIL delta S and I delta T. I is cancelled to give us BL delta S over delta T. If you think that change in displacement over change in time, delta S over delta T is effectively the velocity that this wire moves at. So BLV is another formula for induced EMF that you may need to use. The EMF is also, it's the rate of change of flux, but it's also equal to BLV. Okay, so if we just come back to it, we've got to try and say that this, work out how we can say that this quantity of B times A is now flux. We know that B is flux density and A is an area. So if you multiply a flux density, which is the number of lines of flux in a particular area, and you multiply that by an area, then you end up with the total number of lines of flux in, or that link, that given area. So our quantity of BA actually becomes magnetic flux, because it is quite literally the number of lines of flux that are in or link an area. This is where we've got a new unit and a new quantity. Magnetic flux, symbol phi, here it is equal to B times A, and it's got the units of Webers, symbol letters WB, so it's Webers. And if we think in terms of magnetic flux linkage, then if a coil has got a particular area, you've also got to think that a coil will have a number of turns. So a circular coil will have an area of A, but it's also got a number of turns. So our flux linkage N phi becomes equal to NBA. Lots of people always think, well, why don't the ends just cancel? This N phi, you'd almost need a separate symbol for it. Try and think of it that N phi is a symbol in its own right, and N phi is flux linkage, and flux linkage is equal to the flux multiplied by the number of turns on the coil. So you get the flux linkage N phi becomes equal to NBA. Okay, let's just look at some pictures to put some ideas on this. If you've got this area, this is a circular coil, and it's got an area of 1 meter squared, say, and we've got a flux, a density of B, then the flux, if the flux density is B and the area is 1, then our flux phi is equal to B, 1 times B. Let's just now make it an area of A meters squared. So if our flux is B times A, then we don't know any details about B. B is just B and area is A. So our flux is B times A. And to develop the equation, this is our concept of flux linkage. If we've got a number of turns on the coil and we've got 1, 2, 3 turns, or let's just call it N turns, then our flux now becomes equal to number of turns times the flux density times the area. So the magnetic flux linkage of a coil in a field at an angle to the normal of the coil is N phi equals BAN cos theta. So we've just got to do a little bit of trig to prove why the flux linkage changes to be to use the value cos theta when theta is at an angle theta to the normal of the coil. Let's just look into that. Here we go. This dotted line here is a normal to the coil. Normal means perpendicular. So here you've got, this is where the coil is in this plane, and a normal is in this plane. So if it's at an angle theta, here's the angle theta, and it's an angle to the normal. Then what we're interested in, I've drawn a little vector diagram here. This is the magnetic flux density B. Okay, it's going at that angle. It's at angle theta here. Now the B that we're interested in, or the B that we need, is this side of the triangle, and it's the B that is passing straight through the coil, or at an angle of 0 or normal to the coil. So this is the B that we need. Now, if this is the B that we've got, then the B that we need, we can do some trig, and we can say that cos theta equals adjacent over hypotenuse. So the cosine of this angle equals adjacent over hypotenuse. So I'm going to say that cos theta equals the B that we need divided by the B that we've got, the B that exists. So B that we need is B cos theta. So you can see in the formula, B has got cos theta tracked on the end of it, so that if you've got a magnetic field or a magnetic flux density that is at an angle theta to the normal, the flux linkage you've got is BAN cos theta. When is it maximum? Well, it's at maximum when it's not at an angle, when theta is 0, so cos theta is 1. It's at a minimum if it was exactly through the coil in this plane. Yeah, so if it was lying flat, if you like, then you would get 0 flux linkage. And if you turned it all the way around and went through 180 degrees, then cos 180 is -1. You'd end up with a flux linkage here of a minus value. So this is often used in questions where it talks about the change in flux linkage. Here's some diagrams just to show you that. You can see this is when it's maximum, when the magnetic flux density passes directly through the coil. It's minimum when it's in this plane, and when it's at an angle, you use the formula BAN cos theta. Okay, in summary then, I've covered quite a lot. We know that an EMF is induced when there is a change in the magnetic flux linking conductor. This is the formula we started off with. The induced EMF is BA delta T. It's the rate of change of flux. We then define magnetic flux as being B times A. So magnetic flux linkage was NBA. So our formula at the top of the screen here becomes the induced EMF is equal to the change in flux divided by the change in time. And the one that you're given on the formula sheet is the change in flux linkage. So we've got N phi here, n phi over delta t. And this links directly with Faraday's law. The magnitude of the induced EMF is equal to the rate of change of the flux linkage. So the induced EMF is equal to the rate of change, there's your delta t, of flux linkage n delta phi. Where does Lenz's law come into it? We started off talking about Lenz's law. You may see this equation with a negative sign, and all this, if we bring Lenz's law into this equation, we would say that the direction of the induced current, or the direction of the induced EMF, is always such as to oppose the change that causes the current. So again, referring back, if you bring a north pole into a coil, it causes a north pole on the end that repels. If you remove a north pole out of a coil, it causes a south pole on the end which attracts it. And this means that you've got to do work to do this. You don't get anything for nothing.